Welcome. This time we're going to go through the finite difference method and particularly the central differencing, which gives us a higher order of accuracy, so a more accurate method in general. And we're going to apply this method to solving two of the Euler equations. So it's a slightly more complicated problem than the previous lectures. And we're going to do this using Python, so there'll be a Jupyter notebook that you can download and play around with and modify. So just a reminder that the finite difference scheme we're using, so finite difference is we replace an infinite number of points in a dimension, say x or time as we'll see, with a finite number of mesh points or grid points. So finite difference methods. So here we have a one-dimensional system. So a dimension here we'll label x, and in principle there are an infinite number of points on here, but we choose a finite set that we're going to use. So xn, so we number them with n, and so xn is one of them. We have xn plus 1 and xn minus 1, and then obviously there's more in each direction. So what we do now is we have some function, for example f, that we want to differentiate. So we have a function f, which is some function of x. We want to differentiate it. We want to calculate df by dx, for example, at xn. So the way we do this is by using Taylor expansions. So we have Taylor expansion. So we say f of x is roughly f at xn, plus then all of the infinite series. So we have an x minus xn. So it's df by dx evaluated at that point xn. And then we have a x minus xn squared term with a 2 factorial, d2f by dx squared, again evaluated at point xn, and then this keeps going as an infinite series. So what we do then is we then write the value of f at x minus 1 and x plus 1 in terms of this Taylor series. So we just put xn minus 1 into this formula here, and so we just have that f, let's say xn minus 1 is roughly f of xn, and then this x minus xn, this is, if it's xn minus 1 minus xn, then this here is this distance here we call delta x. That's the distance between grid points. And so this is negative because xn minus 1 is less than xn. So this gives us a minus df by dx evaluated at xn. This is squared, so it gives us a plus. So we have a delta x. So we have minus delta x df by dx plus delta x squared over 2 factorial d2f by dx squared. And then we'll have higher order terms as well. So we have a minus delta x cubed over 3 factorial d3f, which means f by dx cubed, all evaluated at xn. And so the same for f xn plus 1. So this just gives us x f at xn. Now we just have a plus because xn plus 1 is to the right of xn. So we get this direction another distance delta x. So plus delta x df by dx evaluated at xn. Delta x squared over 2 factorial d2f over to xn. And then here we have also delta x cubed. That should be at 3 here. Delta. That's the cubic. So the third derivative of x at xn. And then these both continue, obviously, into higher terms. Okay, so what we're going to do now is we're going to rearrange these equations and combine them together to try and calculate this. So we want to calculate this first derivative So the idea is that we know these quantities, so we know values of f on these points. So we know f at xn, xn plus 1, xn minus 1. And we want to rearrange these equations to find out these derivatives. So we don't know the second derivative or the first derivative here. So we'll first try the first derivative. So one thing is if we take this equation and we subtract, so we take equation 2 and we subtract equation 1, we'll cancel out all the terms with the same signs and we'll add up these terms. And so if we do fxn plus 1 minus fxn, xn minus 1, so this first term cancels out, so we just get a 2 delta x df by dx at xn. And then this term also cancels out, this delta x squared term, and we just end up with the delta x cubed term. So delta x cubed over 3 factorial delta x cubed, okay, and so on. So yeah, more terms as well. Now we can just rearrange this, divide through by 2 delta x, and we just end up with df by dx evaluated at xn is approximately f at xn plus 1 minus f xn minus 1 over 2 delta x. So that's the value we want. This is the expression we're going to use. This is the central differencing. This is central. So it's central because we're using, in order to calculate a derivative at xn, we're using points either side, so symmetrically to both the right and the left. But there's an error associated with this, which is the other terms that we missed out. And so here we have a term here where we divide it through by 2 delta x, so we have a delta x squared, 3 factorial, d3f. And we have higher order terms as well. So this is the error. That's the error in the method. When we make this approximation, we have these other terms we've missed out. It's a second order method because here we have a second power of delta x. Second order in delta x. Okay, we can do the similar thing for the second derivative. So now if we look at these expressions again, so equations 1 and 2, if we now add up these equations, we can use this to calculate the second derivative term here, so this d2f by dx squared. Again, the first derivative term will cancel out, and this first term f of xn will add up. And so we can just write down and use that to get a second derivative term. So we have so f at xn plus 1, so now plus f xn minus 1, and now the first term adds up, so we have a 2f xn, the first derivative term cancels out, and so we just end up with the second derivative term. So we have a 2, then we have a delta x squared, 2 factorial, d2f by dx squared. And the next term, the cubic term will cancel, so we just end up with a quartic term, so 2 delta x to the 4. And then d4f by dx4. Okay, so now the same as before, we can just rearrange this equation. So we know all these quantities, f of xn, xn minus 1, xn plus 1, and we rearrange it to find this d2f by dx squared. So we have d2f by dx squared is approximately, now we have f xn plus 1 minus 2f xn plus f xn minus 1, and just divide through by delta x squared here. that's the second derivative, central differencing. So different second derivative. The error here, again, we just divided through by delta x squared. So we have an error which is, so we have 2 delta x squared. So we start with the delta x to the 4. And put this term. So this is also an error term. This is the error. And it's a second order method as well, because of delta x squared. Okay, so now we're going to apply these methods. So we're going to apply in particular this central differencing term, or central differencing approximation, to solve the one-dimensional Euler equations. So we're going to do 1D Euler. And we're going to, for now, solve 2 equations. So we're going to solve the momentum equation. So du by dt plus the inertia term. So this is the total convective derivative term. And we have a mass density, and then we have a pressure gradient. So P is pressure. So as a reminder, so this is pressure. And this is mass density. And the other equation we're going to solve is for this pressure. So we're going to solve dP by dt. Grad U. And then here we have a minus gamma, where gamma is the ratio of specific heats. P times divergence of U. So U is the flow speed. The flow speed U, and this is the pressure. Pressure P. Now for now, there's this rho in this term here. For now we're going to assume that the mass density is small. The variation in the mass density is small. And so we're going to assume that this is roughly constant. It doesn't add any more real difficulties to the model, but it just makes it shorter. So we're just going to solve 2 equations for now. We can make it more complicated later by adding the third equation. I'm going to solve this in 1 dimension. So we only solve one component of U. So in 1D, so U is just U in the x direction times the x unit vector, and so this becomes an equation for Ux. This becomes a d by dx. Okay, so this is a Jupyter notebook. Hopefully you can download this and have a look yourself. So there's a bunch of imports we're using. The most important one is we're using this SciPy integrate, so OTE int function. This does the time integration for us. So at the moment we're kind of assuming this is a black box and just doing the spatial derivative approximations. I'm using NumPy to get a bunch of useful routines. I'm going to show you very shortly. So as just covered, looking at the central differencing approximation for the first derivative, so any function f df by dx is approximated using this central differencing formula, here with a constant grid spacing, or spacing between mesh points. And so first we'll define that function. So d dx is a function we're creating which takes an array of values. So these are these quantities f and a constant dx. Now what this does is this uses the NumPy roll function, which shifts every value in f 1 point to the left or 1 point to the right, depending on the sign of this. So -1 or +1. If you play around with this function a little bit, so put an array into roll, you'll see that this is basically f at n+1, and this is f at n-1. And so this is the central differencing formula up here, with this constant dx is delta x. Now we're solving this equation, so it's 1-dimensional Euler equations, just the ones I just wrote down, except now this is just for ux, so just for the x component. So we have du by x by dt, and then here we have the advection term, and here we have the pressure gradient dp by dx, and then the pressure equation. And appearing here is this row, which I'm going to assume is a constant called density. And then out of these equations, I've shown in a previous video that you can get the sound speed. So there's a wave we expect, which is the sound speed. Now I'm going to choose the parameters here so that sound speed is equal to 1, and the length of the box is going to be 1. And this just makes things easier because the period of the oscillation should be 1 as well, and so we know what to expect from the waves in the system. So there should be an oscillation which has a period of 1, length is 1, and we expect speeds of 1. Just keep everything simple for now. So I said that the length of the domain is 1. We have 50 points along that domain, so 50 mesh points. This I've just defined is an array, so it uses a range from NumPy, which is there's 50 points long, and we divide by n, so this goes from 0 to length. So the x starts at 0 and goes to a little bit less than length, and then it wraps around to the other side. Defining density is equal to 1, so just for this formula here, and this gamma here is 5/3. So then this part here, this is a function we define, which is going to calculate the time derivatives. So this whole function takes the evolving quantities called f and the time, which we're not going to use in this case, but we have to have an input there. Now f here is going to be a long array of all the values that we're solving. So we have 50 points, and on each mesh point we have a velocity and we have a pressure. So we have 100 values to solve, and so this will be an array of 100 values. The first 50 will be the velocity, and the second 50 will be the pressure. And so what this does is this calculates the length of f, divides by 2 to get the number. It's a little bit redundant because we've defined it up here, but this is a more general way. So if we gave this a different array, this would still work. From this we get the length and the spacing between grid cells, and then this is where we take values out of f. So ux is the first 50 points, or first n points here, and pressure is the last 50 points. And then these lines here, this is the main implementation. This is the actual equations. So I'm just defining this as just a variable, so it's going to hold an array of values. And these are the equations. So we have dux times dux by dx. So this is the derivative of ux. This is the derivative of pressure, and divided through by density, this constant, which is here just equal to 1. But you can change this and see what effect that has. And then we have the pressure equation, which again, the ux dp by dx. These are all just using the central differencing approximation that we defined above. And now, because the quantities we're evolving came in as one array, we return them also as the time derivatives as one long array. And so here we have dux by dt we've calculated, and dp by dt. We just join them together, and so there's ux first and then pressure. And this is because this is the order they came in, so that ux and then pressure must be the same as this order. And that's the main. That's it really. That's the main function. The rest is setting up the initial conditions. So what do we want to start with? So for now I'm starting with 0 velocity, with just a bunch of zeros which has the same shape, so the same size as the coordinates, and pressure which has a constant background. So I've chosen this to be 3/5 because then the sound speed is equal to 1, because density is equal to 1 and gamma is 5/3. And then we add a small sinusoidal perturbation. So it's just 0.1 the magnitude, and then sine obviously has a single period, because x is going from 0 to 1, so this goes 0 to 2 pi. Okay, so then we calculate the times that we want to get an output. So 0 is the initial time, and then we expect the period of the wave to be 1, and so the last time here is 1, and so the solution at the end should look the same such as the solution at the start. We should have an oscillation which moves around but then ends up back where it started. And so this is the time integrator, we give it the equations, the function we defined above, which solves the equations, the initial conditions here, which again is the same order, ux and then pressure, and this is this array here of times that we want the output. So we just run that, and then see it just runs almost instantly. And this value, this thing here is just plotting using matplotlib. So we loop through every value every time, so we get the index and the time itself. We get the result, which is the array returned here, and we take out the velocity values and the pressure values. So again, the same order, so that we have the velocity first and then the pressure, and then we plot. So it should get one line for every time, and that's what you see below here. So this line here is the sine wave, and then the other line, which looks a little bit squashed, is the last time. So you see the wave has oscillated. It's gone from the peak down to the horizontal, then reversed after t equals 0.5. It's reversed like this, and then after time is 0.75, it's come back to horizontal, and after one period, it's ended up almost back where it started, but not quite. So you can see what affects this, and one of the important ones is this size of perturbation. So when we derived the equations for waves, we linearized the equations, and we made the assumption that the perturbations are very small. So if we make this even smaller, change that, you see now the agreement becomes much better. So now the initial and the final solutions are essentially overlapping, and so if you make a small perturbation, you end up with essentially a very good approximation to a wave.